Okay, re-explaining the yellow labeling. The 1.6, well, let's go with the negative 30 centimeters to 30 centimeters is the range of the y values. Okay, so negative 30 centimeters would be here, correspond to the y value here, plus 30 centimeters here. If I multiply that by a sine function, I get a function that goes from negative 30 centimeters to 30 centimeters. So I go 30 centimeters multiplied by the sine of something. Now, I have to figure out what something this is, but whatever this something is, if it's a function that has a variable that goes through at least one cycle of the sine function, then we know that the value of the sine function will go from negative 1 to 1, and when multiplied by 30 centimeters, we'll get a y value that goes from negative 30 centimeters to 30 centimeters. And we've already explained that this could model a pendulum. Actually, at 1.6 seconds and 30 centimeters would be a really, it wouldn't be exactly a low amplitude pendulum, but we don't worry about that. Okay, so we see that the 1.6 second labeling corresponds to the phase of 2 pi, or 2 pi radians. So 1.6 seconds corresponds to, and I might want to put the phase word in here, the phase 2 pi radians. If that's the case, then how many radians does 1 second correspond to? Well, it's more than 1 second. It corresponds to 2 pi radians, so it's going to be less than 2 pi radians in 1 second. And it turns out it's 2 pi over 1.6 radians in 1 second, and that's a simple proportionality, and it's just that simple. So that's pretty obvious. I hope that's pretty obvious. Then, if you have t seconds, then you're going to have t times this many radians, aren't you? So if you have 4 seconds, you'll have 4 times 2 pi over 1.6 radians. So the t seconds corresponds to 2 pi radians over 1.6 multiplied by t. Okay, now remember that t is a number, just a plain number, because we've already said t stands for the number of seconds, right? Now, if t is our time, then we're not saying t seconds, so that our time would have to include the unit seconds. So if t is a time corresponding to 4 seconds, then t has to be 4 seconds, whereas in this case, t just had to be the number 4. If t is 4 seconds, then if we were to multiply 2 pi radians over 1.6 times t, we would get a certain number of radians times seconds, not a number of radians, not something we could take a sine of. The sine will operate on a phase in radians. So we have to have a second down here to divide the second that goes along with our value of t, the unit of our value of t. So we have now 2 pi radians over 1.6 seconds multiplied by t. And if you do the arithmetic, that turns out to be 5 pi over 4 radians per second times t. 1.6 is, well, you could say it's 16 tenths, and it's 8 fifths, and then you do reciprocal 5/8 and do the arithmetic of the fractions, and you end up with 5 pi over 4. This is your phase at time t. This is what you apply the sine to. So now, it's going to be 30 centimeters times the sine of 5 pi over 4 radians per second multiplied by t. Not a totally trivial idea, not that simple of an idea to digest, but you do need to digest it. So let's look at another example. I have 1/60th of a second here at the 2 pi phase, okay, which means that this cycle now, according to this labeling, is requiring only 1/60th of a second. Now that corresponds to the voltage that's supplied to your house by the power company. It's 60 cycle voltage, 60 cycle power. Okay? Voltage is not the same thing as power. Current is not the same thing as voltage. Current is not the same thing as power. Voltage is actually I'm sorry, power is actually equal to the product of the voltage with the current, and the current is something that you get if you plug something in to your voltage source. And that's all I'm going to say about it. There's all kinds of confusion about what that means. A little confusion here. These numbers don't really correspond to the voltage in your typical cycle. Your typical cycle has an average voltage of 120 volts, not a peak voltage of 120 volts, but I didn't want to get that technical. But just a little disclaimer, this isn't an accurate depiction of the voltage of the 120 volt power that's supplied by your power company. Okay, anyhow, with that disclaimer, let's go on and do a model. Okay, well, 1/60th of a second corresponds to a phase of 2 pi radians. So again, I'll say that corresponds to 2 pi radians. So dot 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 the phase at time t is what? Well, we divide the 2 pi radians by the 1/60th of a second to get the number corresponding to this number. That's incidentally called an angular frequency. We don't need that terminology right now, but you get what's called the angular frequency of the cycle, and that term could use some explanation a little bit later. It's going to be 2 pi divided by 1/60th, which is going to be the same, as you can verify, is 120 pi radians over second. If you divide 2 pi by 1/60th, you multiply 2 pi by 60, you get 120 pi. So it's 120 pi radians over seconds, okay? And that's what we multiply by t. The reasoning here is identical to the reasoning we used over here. The only difference is the numbers that go into the process. Okay, struggling for words today, I'm sorry. Okay, now if we want y to go from negative 120 volts to plus 120 volts, then y is going to be 120 volts multiplied by the sine of our phase angle. Okay, our phase here then is 120 pi radians per second times t. Not sure it was wise to try to rub that out, but let's see if we can make the best of it. Okay, so there is our model for the labeling, where the period of the sine function is 1/60th of a second, and the amplitude or the range of the sine goes from negative 120 to 120 volts. That would be an amplitude of 120 volts.